Secure communication using quantum key distribution, which in principle cannot be eavesdropped. Combining distant telescope to form one much more powerful telescope. Or combining small quantum computers to form a larger quantum computing cluster. And many more. These are the use cases of the quantum internet. Quantum internet enables transmission of quantum bits, qubits, between any two quantum computers in the world. Qubits are different from classical bits. They can be 0 and 1 at the same time, and there is a mathematical proof that they cannot be copied. Qubits and all operations on qubits can be represented by matrices and vectors, but this vector space grows exponentially with the number of qubits. Therefore, the simulation time on a classical computer grows exponentially too. The quantum internet simulator was written in Cython language, which is actually a superset of Python programming language. The Cython code is compiled into C code and was designed to give a C-like performance. The idea was to write the CUDA C code called from Cython code and offload the operation on GPU. The two most consuming suitable operations were identified: the matrix multiplication and Kronecker product, the both using dense or sparse matrices. The C code can be called from a Cython without copying matrices, but to compute it on GPU, the data have to be copied to and from GPU. But unfortunately, many benchmarks showed that for used sizes of matrices, only copying data to and from GPU is more time consuming than computation on CPU. After these results, we focused on inner and outer vector space padding, which is using the Kronecker product operation. On the images from profiling our example, we can see that for 6 qubits, the inner vector space padding consumes more than 50% of computing time, and for 20 qubits, the outer vector space padding consumes more than 50% of computing time. But what is important? One matrix in this operation is always an identity matrix. Therefore, as we can see in the example of outer vector space padding, we actually don't have to compute Kronecker product because we can only copy data and create a new bigger matrix. We can see some pattern and we have to compute only indices to new matrix. The ratio between zeros and non-zeros is quite big in the output matrices, and with bigger matrices it actually rises. Therefore, the output matrices are sparse matrices, and the zeros in our example colored black are not stored. On the other hand, the inner vector space padding is slightly different. There is an operation between identity matrix and dense matrix, which is split into smaller matrices, and then the Kronecker product is computed separately. Then these matrices have to be stacked together to one output matrix. But here we can see nearly the same pattern, and we can compute indices from the original matrix without splitting it and then stick it together. These operations were written in C, and computation time of our simulation example is 2.5 to 3.5 faster, depending on number of qubits and number of iterations.